Hello dear students, let us prove a theorem and then let us graph the ln of x. So the theorem has two statements. First one, limit x tends to infinity, ln of x is infinity, and limit x tends to 0 plus ln of x is equal to minus infinity. That is, whenever x is larger, if this is an x-axis and this is our y-axis, and this first statement A says that whenever x is larger, then it is infinity, converges to infinity, and whenever the x tends to 0 plus, that is x is approaching from the positive side to the origin, then the value ln of x converges to minus infinity. And to prove the A part, we are taking ln of 2 raised to n. So by definition or by property of ln, we know that ln of 2 raised to n is n ln of 2 for any positive integer, and ln of x is a positive function. It is always positive. For in particular, ln of 2 is greater than 0, and here we have n ln of 2, and this is a positive quantity. ln2 is a positive quantity, and here we have n into a positive quantity. So whenever n converges to infinity, we have this n into ln2 converges to infinity, and hence ln of 2 raised to n converges to infinity. This 2 raised to n is a particular value for x, and ln of x is always increasing function. To show that it's an increasing function, it is enough to show that its derivative is positive. That is, if we are taking our f of x as ln of x, and then f dash of x is its derivative 1 by x. F dash of x is 1 by x, and it is positive since we are taking x belongs to 0 infinity, since ln of x is defined only for positive values. Therefore, since this f dash of x greater than 0 means ln of x is an increasing function. So it is an increasing function. 2 raised to n is a particular value. So as n tends to infinity, since ln of 2 raised to n converges to infinity, we have limit x tends to infinity, ln of x is equal to infinity. That is, ln of x converges to infinity as x tends to infinity. Now to prove the second part, obviously we are using the first part, and we are taking t is equal to 1 by x. So whenever x converges to infinity, whenever x converges to 0 plus, we have t converges to infinity. That is, whenever t converges to infinity, x converges to 0. Also, when x converges to 0, t converges to infinity. So we have to prove, we have to find the value limit x tends to 0 plus ln of x. We started with that. Limit x tends to 0 plus ln of x. X tends to 0 plus means t tends to infinity, and x is 1 by t. That is, limit t tends to infinity ln of 1 by t, which is equal to limit t tends to infinity ln of 1 by t means ln of 1 minus ln of t. ln of 1 is 0, that is 0 minus ln of t, that is minus ln t. Limit t tends to infinity minus ln t, which is equal to minus of limit t tends to infinity ln t. In A part, we proved that limit t tends to infinity ln t is infinity, so this is minus infinity. Therefore, limit x tends to 0 plus ln of x is minus infinity. So let us graph the natural logarithmic function. Here we take f of x as ln of x. To draw a function or the graph of a function, we need to know about the domain and whether it is continuous or not, whether it is decreasing or it is concave down or concave up, such things. So first one, we know that domain is 0 to infinity, interval 0 infinity, and since it is differentiable on open interval 0 infinity, that is throughout the interval it is continuous, that is the function is continuous throughout the domain. The third one says the first derivative is 1 by x, which is greater than 0, since x is always positive, the domain is positive, which means f is an increasing function. And to know the whether it is concave down or concave upward, we are calculating f double dash of x, that is it is minus 1 by x square. Since x square is a positive quantity, it is always positive, that is minus 1 by x square is always negative, that is graph of f is throughout it is concave downward on 0 infinity. Also by above theorem we know that limit extends to 0 plus ln of x is minus infinity, and limit extends to infinity ln of x is infinity. To draw, we take some arbitrary random values for x and we calculated corresponding f of x, that is corresponding ln of x. The last theorem says that whenever x is infinity, then ln of x converges to infinity, and whenever this x approaches the origin from the positive side, that is limit x tends to 0 plus ln of x converges to minus infinity. Since f dash of x is positive, we can see that it is an increasing function, and since f double dash of x is less than 0 means it is a concave down. Hence we can draw ln of x as shown.